introduction and good afternoon, everyone. So in my presentation, I'm going to showcase the potential of the modeling strategies developed by the computational structural mechanics group at Imperial towards an objective multi-level assessment of masonry arch bridges. So I will start So, in the main part of the talk, I'm going to focus on results of numerical simulations, where I will stress the prediction of the 3D characteristics of the response, and then I will consider comparisons among results obtained by models based on different representations for material nonlinearity in masonry. And then, of course, at the end, I will draw conclusions indicating directions for future research. To achieve an accurate response prediction, we should consider the use of 3D models, explicitly take into account the different structural and non-structural parts, including their nonlinear interaction. So current assessment, though, is typically based on simplistic methods for different reasons, for practicality, for computational cost. And these methods are considered simplistic 2D representations of arch backfill of the arch backfill interactions, and using different models to take into account material nonlinearity in masonry. We found that this may lead to inconsistent results, and in many cases also may lead to unsafe predictions. So for this reason, there is a need of developing a multi-level assessment method where simplistic approaches are categorically safe. And this can be achieved by linking the predictions of simple models to the results one may get using validated high-fidelity models. So the focus here will be on illustrating the potential of using high-fidelity models and how this model can be used to study 3D interactions leading to the complex response of masonry arch bridges, and also can be used to calibrate simpler models. So this multi-level approach is taken into account by current guidance documents. It is currently, accepted in the UK, but the main challenge there is the link between the different levels. So as I said before, it's not categorically demonstrated that lower level models can provide safe predictions. So there is still need to link this model towards an objective multi-level assessment approach. So the focus of my talk will be on advanced methods. So I'm going to showcase the potential of the computational strategies developed at Imperial towards an advanced 3D nonlinear finite element modeling of masonry bridges. In this talk, I'm going to consider the response to vertical loading. The models we develop can be adopted also to investigate the behavior under different loading scenarios, including extreme events like earthquakes. So I will go through the basics. I mean, these are quite well-known concepts, but it's better to stress them again. So we will know that masonry is a complex material, is an isotropic material. The behavior is due to the characteristic of the individual components, but also by the masonry bond, the way in which units and blocks are linked by mortar joints. So in masonry arch bridges, we know that the main part of the masonry arches, so different bonds are possible for arches. In the UK, so when we use brick masonry, we can find different bond arrangements, including the structure bond, where we have continuous mortar joints along the circumferential direction, and header bonds, where we have headers, avoiding the continuity of the circumferential joints. Different bonds may lead to different failure modes, where the structure bond may facilitate ring separation, which is a critical failure mechanism to be taken into account. So how we can represent material nonlinearity, as we know, is very important. So it's very established. Typically, we consider masonry as a uniform material. We operate at structural scale when we analyze large structures, typically using finite elements. We assume masonry as a homogeneous material, and we adopt typically isotropic material models. In research and, of course, in practice, especially when we deal with relatively challenging structures. So when we refine the models, we move to the meso or micro scale. So we consider a separate representation between the different parts and the interaction between units and mortar joints. This is typically adopted for detailed simulation at a small scale. So the convenience of the meso micro scale is that the material characterization can be performed at the level of the constituents. So in the case of bridges, we can take cores, we can investigate, we can test cores, and to achieve bond and shear strength characteristics, as well as compressive strength of the masonry material, which is obviously a very important information to be able to develop consistent numerical models. The disadvantage, of course, is the computational cost, which may be excessive, preventing the adoption of this detailed method to the analysis of large structures. So the developments in our group. So in our group, we consider different type of methods. We have a well-established mesoscale approach for masonry. We adopt it to represent the behavior of masonry at bridges. The masonry parts are represented by a mesoscale method, which enables a precise representation of masonry bonds for the different parts, arches, spandrel walls. The backfill is modeled as a continuum model, allowing for the frictional and cohesive characteristic of the material, and also the physical interfaces between the different parts are modeled using nonlinear interfaces. So this is well established in the literature. Nonlinear interfaces enable separation, shear sliding. The characterization at the strength level can be achieved via simple material tests. Our interface material models take into account also open enclosure of cracking and the plastic frictional behavior under monotonic excited loading conditions. So the counterpart we developed and we are using today to showcase the potential of the method is a more standard macroscale approach. Of course, it's more efficient. It requires a reduced number of freedoms, and it is implemented also in commercial finite element codes. So, of course, it is isotropic. It allows for damage, but it doesn't allow for the anisotropic characteristics of the response. And importantly, it does not allow a proper representation of the shear behavior. It doesn't take into account the frictional characteristics and the interlocking. So in this macroscale model, the backfill and the interfaces linking the masonry parts in the backfill are modeled in the same way as for the detailed mesoscale approach. So in our models, we improve computational efficiency using a domain partitioning approach in combination with parallel computation and the use of high-performance computing capabilities at Imperial. I don't spend more words on this because Professor Risodini is going to give a detailed presentation on this method tomorrow. So we developed our methods in combination. So when we deal with a large structure and we want to focus on a specific section of the structure, we can adopt a mesoscale approach, and the remaining parts of the structure can be modeled using a more standard macroscale method. This is needed especially when we deal with large violets. So relatively recent development to facilitate the generation of the models, we invested a substantial amount of time in developing a quite powerful a piece of software in a Rhino grasshopper environment, which enables a parametric generation of masonry bridges and viaducts with complex geometries, taking into account the separation between mesoscale and macroscale representation for the masonry parts, taking into account a variety of different bond characteristics. It takes into account also internal features like internal spandrel wall, backing, backfill for the inner parts of these complex structures. So, I want to acknowledge that the computational developments have been implemented in adaptive, a finite element code, for advanced nonlinear analysis developed at Imperial College, and we need to acknowledge the contribution of several researchers, including 3 researchers here in the room and giving other presentations like Enrico Tubaldi, Corrado Chisari, and Walter Pantò. They worked with us for a number of years during their Marie Curie fellowships at Imperial. So now we move to the more interesting part of this presentation. So parametric study. Of course, we started with a model validation because we need to trust our model, we need to trust the accuracy they provide. We look at full-scale experiments conducted in the past on a 3-meter span bridge with an arch with stretcher bond, and in parallel to the physical test on the large arch specimens, material tests were performed, which are essential for the calibration of the properties. So we developed a detailed, a mesoscale model. You see the bond for the arch and then the spandrel wall are properly represented, stretcher bond and English bond for the arch, English bond on the spandrel wall. So we managed to achieve accurate response prediction with good comparison against the experimental curve. And importantly, the model enables an accurate representation of the cracking pattern at failure, damage in the spandrel wall, separation between arch and spandrel wall, and different complex cracking in the arch, a combination of radial cracking and ring sliding. And of course, damage in the spandrel wall. In this case, you see the out of plane deformation of the spandrel wall is limited, so which indicates a reduced 3D behavior because the structure were loaded by edge knife load applied throughout the whole width of the bridge. So we validated the model. This is just an example, but we performed several other validation examples. So then we confirm the accuracy of the predictions. And now in this talk I would like just to showcase, the potential of the method in comparisons also against the prediction obtained by simpler techniques. So we consider a range of realistic single-span masonry bridges. You see with 3 and 5 meter span, 2 ring, 4 ring, header, stretcher bonds, and you see the computational cost. This is just for a 3 meter width. We consider also 9 meter. But for a 3 meter width, we move to 2.5 million degrees of freedom. So it is a significant amount of freedoms. The representation is very detailed, but this is just obviously not for a practical application. It's just to provide baseline response predictions one can use to compare against more efficient models to understand the limitation of more efficient models towards an objective multi-level assessment. So how we apply the load? We consider a typical axle load, just one wheel. We consider spread through the surface field. So we consider then a patch load. And where the patch load is applied at different positions along the span length and the width of the arch. So you see then we investigated the different scenarios to shed some light on the response. And what we consider, first of all, a study to investigate the effects of spandrel walls. So how we conducted this study? The high fidelity mesoscale model and a model with the same arch, same backfill, but not spandrel wall. But the spandrel wall is fully restrained laterally, so we assume that we have full confinement, but not the contribution of the spandrel walls in the longitudinal direction. So then we apply the load, a generic load position, mid-span with width, comparison, detailed mesoscale, blue card, mesoscale with no spandrel wall, red card. So it shows that the spandrel wall contribution in this case leads to higher prediction, and then the cracking of the spandrel wall moves the numerical curve with spandrel walls towards the curves of the model without spandrel wall. So, and you see, it's important to note that in this case we don't have notable out-of-plane deformation in the spandrel walls. Spandrel walls are still capable of confining the backfield, and so the response converges towards the response of the model with fully confined spandrel wall. So at the loading position, nearer to the spandrel wall, okay, you see a more complex tracking pattern. Importantly, we reach the peak, considering the spandrel wall contribution, quite early. Then we have a cracked spandrel wall. The response converges towards the response of the model without spandrel wall, but then you see out-of-plane displacement of the spandrel wall, lack of confinement, softening response. So in this case, if you don't take into account spandrel wall, you don't have a safe estimate, because you assume full confinement of the fact field, which is not always guaranteed. So, and this is true also for other scenarios. Okay, you see the model with spandrel wall leads to a reduced capacity for this reason, because of the out-of-plane deformation and cracking of the spandrel wall, preventing this component to confine the backfield. So, and again, if you consider different geometries for the spandrel wall, thinner spandrel wall, again, a reduced capacity. Why? For the same reason. Out-of-plane deformation, cracking, and inability of the spandrel wall to confine the backfield, which again stresses the importance of allowing for the 3D characteristics of the response. Typically with 2D models, we disregard this interaction. We assume the backfield fully confined, and so we achieve a prediction, which in some cases may be unconservative. So effective with study. So, as I said before, detailed models can be used also to calibrate more simplistic 2D models. How? Establishing an effective width for simplistic and efficient 2D recollections. Currently, current guidance indicates effective widths based on basic geometrical considerations, considering largely the contribution of the depth of the backfield and assuming a certain distribution of the load from the top of the roadway or railway down to the arch. So it does not depend on the material characteristics, it doesn't depend on the 3D behavior of the structure. So in our study, what we did, we ran a simulation with full 3D models, we compare against one 3D model, a 2D model, where the 2D model is a 3D model assuming 1 meter width, with a full confinement of the backfield. In this case, we disregard the spandrel wall, so the 3D models are models with archer and backfield only, because the focus here is on the spread of the load to the backfield and the consideration of 3D effect via a 3D model without taking into account the spandrel wall contribution. So our study found that the effective width actually depends on a number of factors: load position, backfield characteristic, 3D arch behavior, but also material characteristics of the arch, which is quite interesting. So we compare our study, moving the load, different position with different widths, and the comparison is against a simpler 2D model. So the results we got, of course, we compare the 1 meter width 2D model against the 3 meter, 6 meter, and 9 meter width. When we see that the response at a certain point converges, so if we keep widening the arch, we don't increase the capacity of the arch. So, and this enables to define the relationship between 3D and 2D models, so the proportionality, which actually is effective width. And we see that it doesn't change much a different loading level, and actually in this case we found the value is not very different from the value recommended by the standard, which is fine. It's fine until a certain point. So if we consider, for instance, weak bricks, right? In the previous simulation, we assumed strong bricks, as in the original experiments. Engineering bricks with very high compressive strength and tensile strength. If you assume weak bricks, which are found in several old masonry bridges, definitely in the UK, the response is quite different. Why? Because the 3D effects develop, right? The transverse bending take place, and what we notice is the formation of longitudinal cracks, strong brick cracks mainly along the mortar joints, dead bricks cracks at some point also along the masonry units. And we can find this, the results in this set of numerical curves, the same arch with 3, 6, and 9 meter width. So I'm analyzing the 3 meter one. So after the formation of a first longitudinal crack, second longitudinal crack, a significant drop, third longitudinal crack, basically a separation in a very neat, narrow strip, which indicates, directly a definition of effective width for this case. So this is found in many practical applications. In the UK, typically, when we investigate viaducts, we see longitudinal cracks, mainly due to the presence of internal spandrel wall. So we have an informed decision about effective width, because we see longitudinal cracks, and then we assume the effective width, the distance between two consecutive longitudinal cracks. The problem here, though, is that the formation of two cracks is not far from the peak load, so you don't know in advance the distance between longitudinal cracks. So when you perform the assessment, you need to establish an effective width, which according to the current standard does not depend on the strength characteristics of the material, and in this case is not conservative. So we can look at this interesting view. This is the contours of vertical displacements, a different loading level, so different displacement level, strong brick, elastic response, and then you see we have a formation of a mechanism. So we large, displacements around midspan where the load is applied and radial crack form. But if you consider weak brickwork, so you see how we localize the deformation, because we form a narrow strip, right? And obviously this strip indicates the failure mechanism. So if one considers a 2D model with assumed effective width, may lead to unconservative predictions. So model complexity study is another interesting application of high fidelity models, just to stress the limitations of more simplistic and efficient approaches. So in the first example, right, I consider a relaxation of the mesoscale mesh. Typically when we analyze super large structures, considering viaducts with 50 meter plus span, 9 rings, a number of spans, it's practically impossible, also using high performance computing resources, to use the actual a mesh which represents the actual bond. We need relaxation. So what does it mean relaxation? It means expanding the mesh. So instead of using one solid element for other bricks, increasing the element size. And this can be easily done, and then we can use a stiffness equivalence to calibrate properly the stiffness characteristic, and performing a straightforward calibration, we can assume the same strength characteristics for the nonlinear interfaces. And we try to use this approach, we use in practice several times, and just to investigate the limitations, right, and to assume a certain safety factor, right, for the practical implementation of the method. So you see in this case we have a 3 meter span, so high fidelity, relaxed 2 times, 3 times, 4 times. So obviously freedoms, we start from 300,000 plus, we move down to 49,000. For us it's not much, or Evo may stress that it's too much, but we can carry on this way. So we got an example. So we apply the load, mid-span, quarter width, and you see the prediction of the failure mode is not bad, right? We still have a certain formation of the crack underneath the load and a spread of the cracking. And also the prediction of the peak load is not bad. So we have more or less the same peak load and also the same stiffness. On the other hand, moving the load position, we get not so accurate prediction, especially when we move to relaxation 3 or relaxation 4. where again the prediction of the cracking is not accurate. Again, I'm not saying we cannot use a relaxed model. I'm saying when we use a relaxed model, we need to take into account some safety margin, because these relaxed models cannot achieve the same accuracy or detail mesoscale model. So another simple example here, you see this is a larger span with a number of rings. And now it's an interesting problem. Relaxation throughout the thickness, right? We need to model 4 rings, or we can just model 2. With 2 rings, we still have a longitudinal interface, a conferential interface, which enables us to prevent potential sliding. But of course, the representation is not so accurate. What we achieved, so we achieved that actually with a relaxation through the thickness, the response is completely inaccurate. Is completely inaccurate because the failure mechanism is much more complicated, right? So, and with a relaxation level 2, without we consider relaxation along the length and along the width, but not along the thickness. The results are basically coincident to the full mesoscale, but the relaxation through the thickness leads to this very inaccurate prediction, which when we achieved these results, we were quite surprised, but I think is a good outcome to be considered further. So I move on now to the very final 2 minutes, right? So a comparison against a macro scale model, which is again very interesting in my opinion. So in this case, I remind ourselves a macro scale model. Masonry is modeled as a uniform material. We use a standard dimension plasticity model, isotropic though. So we about the calibration, because it's very important. The elastic parameters are basically the same because we calibrated the mesoscale parameters with the same macroscale parameter. The strength characteristics, we need to make a decision here. It's an isotropic model, we need to choose a direction. The direction we selected for the strength, the size strength, is the radial, we consider the physical strength along the radial direction, which is the bond strength for the arches. So in the macroscale model, we assume that the size strength is the bond strength, which is a decision to be made, right, when we use these sort of models. And the results we achieved are quite interesting. So we started with a stretcher bond. So you see macro scale and mesoscale, the 2 curves are very close. The results are very good, but this is a stretcher bond. So if you consider a mesoscale header bond, so no ring separation, so the header bond prediction is much higher. But here we are talking about not 5%, 10%, we're talking about a quite significant distance between the mesoscale and the macroscale prediction. And we can see in the detail, right? Stretcher bond, we have sliding, diagonal, radial cracking, but not typically continuous throughout the thickness because of the sliding behavior. Header bond, so no sliding, just radial cracking. And of course, higher performance, higher prediction. Macroscale model, it provides, I don't know why, but because we cannot control them, we don't allow for bond. We make an assumption about strength and we trust the model. And you see in this case, the results are quite conservative and they don't reflect the actual bond characteristic of the structure. So moving the load, we achieve the same results. Importantly, when we consider a certain position which is quite critical throughout mid-width, mid-span. So mesoscale model, relatively complex tracking, similar to what Vasily showed us this morning, right? We have some cracking along the width plus diagonal cracking along the mortar joints developing, which is quite a relatively complex, cracking pattern, which takes into which it depends also on the interlocking characteristic of the masonry bond. Macroscale model does not take into account it, and the results we got are very, very conservative. What we achieve here is a sort of punching shear. Why? Because the load is applied above the crown, the level of backfill is relatively shallow, and then we have a localization of plastic deformation and damage just in the close area, and we predict failure. So again, relatively, interesting results and a warning message in using, a macro scale model, especially when the model are isotropic. So conclusions, and I think, in our research, we demonstrated the potential of using high fidelity models, to provide baseline results, right, to be used and to calibrate more simplistic models, and also to gain and improve understanding of the actual behavior of this complex structure. So regarding the use of 2D models, more studies needed to establish, realistic, effective width, parameters, which in my opinion should depend also upon other, parameters, which are not just geometrical parameters. And then limitation of standard macro-scale isotropic model. So there is still a need here to improve, the definition of the description of the material at the macro scale. So we made a contribution in this by developing and enhance an isotropic macro-scale model, which will be presented and used later in a presentation by Professor Cantò. And then we consider also in the past refined calibration strategies, again with Dr. Cantò and Dr. Chiesari, which enables to achieve and improve prediction also when using macro-scale isotropic models. So this concluded the presentations, and of course, thank you very much for the attention.